Welcome to CognitionChunks. This is Tangled Up, Unknotting the Unknot. Explaining knot theory. Note this is coming from a relative novice on this topic who is trying to learn about this topic from GPT. I am not a mathematician or an expert on this topic. A follow-up series to distinct types of math branches. In the intricate dance of mathematics, knot theory emerges as a captivating ballet of loops and entanglements. Let's dive into this fascinating world, where the seemingly trivial becomes profoundly intricate and the abstract touches the concrete. The building blocks, fundamental concepts. 1. Knots and links. Imagine holding a piece of string, looping it around, and then fusing the ends. You've just created a mathematical knot. The catch is, this loop is living in three-dimensional space, a realm denoted mathematically as \math r3 Unlike your regular knots, these mathematical knots are unbreakable and uncuttable. Now, what if you take several of these unbreakable loops and entwine them? You've just made a link, a cluster of knots that can be individually simple or complex, and either intertwined or isolated. 2. Ambient isotopy. Picture two dancers moving gracefully across a stage. If one dancer can transition into the other's position without tearing through the backdrop or merging with the other, they're demonstrating what mathematicians call ambient isotopy. In simpler terms, two knots are ambient isotopic if one can be transformed into the other without cutting or gluing. 3. Knot diagrams. Imagine trying to explain your dance moves on paper. Knot theorists do something similar. They use 2D projections to represent 3D knots. These diagrams display the loops as a series of overcrossings and undercrossings. The challenge is to remember, this is a mere shadow of a 3D object. To navigate these shadows, mathematicians use Riedmeister moves, a set of local diagram transformations that preserve the knot's essence. 4. Invariants. The signature moves in the dance of knots. Invariants are properties that remain unchanged through ambient isotopy. These include mathematical objects like the Jones, Alexander, and Conway polynomials. They're the choreography notes that remain constant even as the dancers change their steps. Choreographing complexity. Advanced topics. 1. Knot polynomials. As composers create variations on a theme, knot theorists develop different types of polynomials to characterize knots. These include the algebraic signatures like Jones and Homfly polynomials. 2. Braid theory. Every knot can be considered a dance of several strands, a braid. Braid theory explores these multi-strand choreographies and explains how braids can close into knots. 3. Hyperbolic knots. The vast majority of knots, believe it or not, reside in a hyperbolic realm. The geometry of these knots offers clues about their topology, the study of properties that remain unchanged under continuous transformations. 4. Kovanov homology. Upgrading from a single polynomial. Kovanov homology is like a complex choreography, consisting of a series of interconnected algebraic structures known as chain complexes. This provides a richer language to distinguish between knots that may share simpler invariants. 5. Virtual knots. Imagine choreographing for holographic dancers on virtual stages. Virtual knots exist in mathematical spaces even more abstract than our 3D world, adding layers of complexity and opening up unexplored territories in knot theory. The grand stage. Applications. 1. DNA topology. Like a ball of yarn, DNA can get knotted and twisted. Knot theory helps us understand how enzymes act like skilled dancers, elegantly unknotting or linking DNA strands during crucial biological processes. 2. Quantum computing. Imagine a computational dance in a quantum realm. By using braids in a 3D spacetime stage, topological quantum computing offers a way to perform fault-tolerant quantum calculations. 3. Fluid dynamics. In the turbulent ballet of fluid flow, vortex lines can form complex knotted structures. Knot theory gives us a toolset to analyze and interpret this fluid choreography. For material science, on a molecular level, understanding the choreography of atomic interactions can lead us to materials with unique, tunable properties, everything from super-strong fibers to new types of polymers. Encore, examples and further study. 1. Unknot, the solo performer of the knot world. While it may look simple, a loop, it poses complex questions. Is it possible to determine algorithmically whether a given knot is, in fact, an unknot? The answer isn't straightforward. 2. Torus knots and more. Like dancers who stick to a certain part of the stage, torus knots reside on the surface of a torus, a donut-shaped space. Examples include the trefoil knot, which is akin to a basic waltz in the world of knot theory. 3. Figure-8 knot and hop flink. These serve as the classic duets in many knot theory performances, illustrating fundamental principles in a way that's both engaging and illuminating. If you're intrigued and want to delve deeper, consider immersing yourself in seminal texts like The Knot Book by Colin Adams, or explore the world of virtual knots through the work of Lewis Kaufman. So, whether you're a mathematician, a physicist, or just someone intrigued by complex systems, the world of knot theory has something to offer you. It's a field where the depths of abstraction meet the heights of applicability, a realm where every loop and twist holds a universe of possibilities. Welcome to the never-ending dance of knot theory. In a world as intricate as ours, sometimes the simplest of concepts reveal astonishing layers of complexity. Take, for instance, the notion of the unknot in knot theory. At a glance, it's just a circle, a loop with no twists, turns, or tangles. But as mathematicians, physicists, and philosophers alike will tell you, the unknot is a concept laden with fascinating intricacies, both computationally and philosophically. So, sit back as we embark on a journey to unravel the unknot, a symbol of both unity and complexity in the mathematical universe. Basic properties of the unknot, the simplicity before the storm. We start by grounding ourselves in the fundamental aspects of what makes an unknot. To understand this, we venture into the world of ambient isotopy, a sort of cosmic dance where objects in space, including our unknot, can be smoothly deformed into one another. In this realm, every unknot is essentially the same, revealing a profound unity underlying all simplicity. Next, we visit the domain of knot invariants, unique mathematical fingerprints for knots. For the unknot, these invariants are in their purest form. The Jones polynomial, for instance, manifests as a simple 1, and the knot group aligns itself with the integers. And let's not forget the braid representation. In this tapestry of interwoven threads, the unknot sits quietly as the trivial braid, a straight parallel ensemble with no crossings, no drama, but plenty of theoretical significance. Into the labyrinth, computational complexity of unknot detection. While understanding an unknot might be straightforward, recognizing one hidden within a labyrinthine diagram is a computational beast of its own. This is where the heavy artillery of algorithms comes into play. It's an epic clash between man-made logic and mathematical obscurity. First up, we have the normal surfaces theory. Imagine slicing through the knot's surrounding space to create simpler, geometrically distinct regions. You study these pieces, hoping to find evidence that your original knot is, in fact, an unknot. Among the knights of algorithms, Haken's algorithm stands as an ancient guardian, powerful but computationally voracious, gobbling up resources like a black hole. As of my last update, a more contemporary hero arose, Mark Lackenby, wielding an algorithm with a time complexity of \O(n)11, striking a balance between speed and accuracy. Real-world heroes, applications. Now, why should you care about unknots? Imagine the microscopic universe inside a living cell. DNA, those coiled ladders of life, sometimes entangle themselves. The study of unknots helps scientists understand how cellular machinery untangles this complex web. The same logic extends to the mesmerizing world of protein folding, a tale written in the chains of amino acids. On the cosmic scale of things, unknots serve as the trivial loops in topological quantum computing. Think of them as the zeros and ones, the true and false, in an entirely new language for futuristic machines. Beyond the numbers, philosophical dimensions. As we shift our gaze from equations and algorithms, we find that the unknot has been silently teaching us lessons in philosophy. It stands as the mathematical incarnation of identity, echoing the importance of unity and simplicity amidst complexity. But that's not all. Its very existence challenges us to rethink our understanding of transformation, change, and the limitations of our cognitive abilities. The Unknot whispers secrets about the bounds of computational power and the enigmas of Gödel's incompleteness theorems. Conclusion: a paradox of simplicity and complexity. So, what began as a simple loop circles back to reveal a tapestry of computational, physical, and even philosophical wonders. The Unknot serves as a compelling example of how simplicity isn't just an absence of complexity but a form of it, a mirror reflecting the profound intricacies inherent in nature and thought. Through the lens of semiotics and paradox, the Unknot further complicates our understanding of representation and meaning. It invites us to ponder on philosophical paradoxes, such as the ship of Theseus, asking whether identity is preserved through the process of transformation. As we conclude our exploration, let it be known that the Unknot isn't merely a mathematical curiosity but a monumental testament to the enigmatic relationship between simplicity and complexity, uniting mathematicians, scientists, and philosophers in awe and reverence. It's a symbol that compels us to ask deeper questions, pushing the boundaries of our understanding, one loop at a time. Thank you for joining us for another Cognition Chunks. Was this accurate? Did GPT just make up a bunch of stuff that does not exist or does not make sense? Find out next time in the Cognition Chunks follow-up.